Hello, Spark fans, and welcome back to Advancing Spark, where today we're looking at Bloom filter indexes. Oh, doesn't that sound exciting? And actually, when I first heard about it, I was like, really? Like an index in a data lake? That's not a thing. Actually, it's been a thing for a little while. And it's something there's a few different attempts to try and get something in place for. And it's essentially a way of making it much, much more efficient to find a small bit of data, do a single record lookup, the needle in a haystack style query across a vast amount of files in something like a lake. So Bloom filter index is really, really good if you're trying to build a performant data lake. Now, this implementation is based on Delta, so it is part of that kind of Delta file format ecosystem. But essentially, it's just creating a series of additional index files, reference files, on top of your Delta transaction log that then says, probably in this file, it's definitely not in that file. And that's all it is. It's a data skipping mechanism. So when you've got a query coming in that says, hey, I've got 10,000 files, where should I be looking? It goes, you know what, don't bother with those 5,000. You probably want to look in these ones, and it's definitely not in those ones. And that's the kind of thing we're looking for. So it's not an exact pointer. It is not 100% that file is in that particular space, in that particular record. It's not the same as doing a clustered index in a SQL Server, but it is all about that same style of thing, saying, I've got a quite specific filter I'm trying to do on a given query. Can you just tell me which files that's likely in to minimize how much data I'm touching when I do my read? So that is what we're looking at. We'll dig into it and we'll have a look how it works. As always, don't forget to like and subscribe. Hello, if you are new to the channel, check out all the other videos. We do lots of this kind of stuff. And as always, let us know down in the comments what you think. Are you already using Bloom filter indexes? Do you have any best practices from how you get the best for your users in how you're using Bloom filters? Or have you never heard of this and this is an amazing thing that you're going to start using? Just let us know down below. It'd be good to hear from you. On that note, let's get cracking. So, what do we have over here? First things first, there is a load of documentation. So there is built into the Databricks website, there's just a ton of information about Bloom filter indexes. And it's something that has been evolving for quite some time. Now, I heard about it it was only middle of last year I heard people first talking about it, but it's something that I always first thought of, that's going to be really annoying and tricky and hard to implement and maintain and look after. And it sounded fairly complex. And it's only when I dug into it and went, oh, it's really easy. It's really, really easy. And so as soon as you start putting it in, as soon as you start implementing it, it is quite an easy performance gain to get. So there's a load of information in normal Databricks style. They've gone very academic in explaining how this works under the hood, what the approach is, and all that kind of stuff. And it seems a little intimidating when you first look at it. Essentially, it's going to create some other objects. So alongside your Delta table, it's going to create another folder structure. It's going to put in there for each and every Parquet file in your Delta table, it's going to create another Parquet file that has essentially a binary reference as to these are the different stats for different records appearing in that particular file. So essentially, it's making a little lookup that then sits alongside every Parquet file in your table, so that when it's doing a scan and saying, right, which files should I look in, it reads those additional files first, decides which of your main Parquet files it should read, and then uses that in its execution plan. And then there's just lots of information about the settings and how it works. So it's enabled by default. You can turn it off if you want to. Don't know why you would. But the main thing is, that's all it is. So you can use it via the SQL interface. Say, I would like to create, whatever you want to call it, an index on my table. You tell it the columns that it should do, and then you need to give it the options. And the options is where it gets a little complex, and there's a few more settings, and there's nuance to do with how you actually set that Bloom filter up. So main things that we're dealing with, FPP, it's the false positive probability, and you got the number of items. Now, there's a bit more info you can get down here, I think. Did it have more info? Oh, it didn't. That's another page. And that essentially goes into, all we're trying to do is manage the chance you're going to have to read more data than you should. That's the worst case scenario. The absolute worst case scenario when you put a Bloom filter index in is you read more data because you weren't sure whether or not the record was in that file or not. What it doesn't do is mean you might accidentally skip a file. So you're always going to get the right data. It's just whether or not it does the most performant one is based on a percentage of probability, and it's up to you to decide how accurate you want it to be. Do you want your Bloom filter index to be huge but incredibly accurate? So you're going to narrow it down to exactly the right files, but each and every time you add new data, it's going to take longer to write because it has to build this fairly complex tree of all the data that's in there. Or do you want to get like a best endeavors? Most of the time we'll read main files. We might occasionally read one or two extra files, but you know what? It's quite simple to maintain and it's nice and easy. So that FPP, the false positive probability, is what is your tolerance for how long it takes and how costly it is to maintain versus the chance of it occasionally making you read more data than you need to. And that's a little seesaw that you need to get right. And it's kind of it depends on your data. It depends on how you're going to work. All of that kind of stuff. You've then got a number of items, the number of distinct items a file can contain. So again, that's kind of another setting is about how big the file should be, how expensive it is to maintain, how optimized it makes that. Now, honestly, I've not done a huge amount in terms of that lower level configuration. And it does kind of come down to, it depends kind of what your data looks like. It depends how many rows you have, depends on the cardinality of the columns that you're putting into it. It's very much it depends. But certainly you have those levers that you can play with to get the right level of performance versus size versus, I guess, maintainability and complexity. Yeah, words. Cool. So they are the different levers that we've got. But essentially that's about it, right? So we create an index, you put it on a table, you choose which columns it should go on. And then you choose what your different percentage probabilities are. And then that's about it. And then it starts working. So we'll go through, there's a couple of sample notebooks that Databricks have provided, which we can use to evaluate it and have a look at how that works. I'm going to grab up the actual lake so we can have a look at what's going on underneath. But let's go from there. So I'll ping a link to obviously these details and everything that's going on there. And the thing that the Databricks guys have shared is this Bloom Filter Index demo notebook. So it's a SQL notebook. So everything is running in the SQL language environment, and you can do everything from there. So I've just taken that, I've imported it into my local workspace. I've changed one or two things. It's doing it based on 1 billion rows, and I'm like, you could probably do it on 100 million and we'll get some decent results. But I'll step through what that looks like. The other thing is I've changed this, so rather than, by default, this notebook runs in DBFS, so it creates a table inside the Databricks file store, and you can't really nicely see what's going on underneath. I've just created it in my lake, so I can actually go and have a look at it, see the folders, see the extra files it creates, and all of that good stuff. Apart from that, it's the same notebook, so you can just grab that from the Databricks site and work through it. So what is going on in here? So first things first, they've just made sure the configuration is turned on. Now that is enabled by default, so you don't have to turn that on, but that's just we can check, make sure it is definitely enabled. We're all good. Those two are enabled. Okay, it's then creating a Delta table. So we've got this Bloom test table. It's got a load of just random data in there. It's creating it as Delta format. Now I am actually using 8.1, so I don't need, if I didn't specify that, it knows it's Delta because now Delta is the automatic format. But I'm specifying it because you should always. Okay, but that's good. So I've done that in advance. We can go and have a look at that table. So let's just grab that up on this side. Okay, so we've got in my root folder, in my lab, we've got my Bloom table, and we've got the Bloom test. So it's just a Databricks table, creates the Delta log, all that kind of stuff. So you can see I have done some updates, and they're as part of this particular notebook. So this creates an empty table, and then that next step is adding in that Bloom filter index. So at that point, when you create that, we're saying, I want to create it, we're going to call it Bloom filter, index, going on that table. We're doing that on the SHA column. So you'll see in terms of the different columns I've got in here, one of them is we're just going to do a SHA hash on something. And we're essentially saying that's the column I want to index on. So a little bit like Z ordering. So Z ordering where we're saying, take the data, recombine it into more efficient files based on a particular key. Try and co-locate values or records that have the same value for this key into the same files. So that's what a Z order would do. This is saying on top of that, create an additional index structure on top of this column, which helps us even better locate files within those optimized files. So we're saying we want it to be, we're going to optimize for people querying on that SHA column. And that's important, right? So the same as a non-clustered index, if you go in the SQL Server and you write a query and you put a filter on it on a column that doesn't have the non-clustered index on, it's not going to hit that non-clustered index. You have to have indexed on the column that you're trying to increase performance on, otherwise it's not going to do anything. And they've got some example queries just to prove that fact. Okay, so that just at that point, you've got basically a shell. So you've got an empty table and you've got an empty index. In this case, we said there's a 10% chance of a false positive, and we're optimizing it for 15 million objects. It's kind of like a balance. This is kind of the default. I've kind of kept it with that to see how it works and see what it looks like. So there's then a little data generated just to give you some demo data. It's going to truncate the table. It's going to do a little CTE to kind of just generate some hashes and that kind of thing, and it inserts it into it. So it just ran this, pushes it out. This was doing it for 1 billion. I changed it there and went, just make it 100 million. Don't go crazy. And that goes in, inserts a load of rows. So I've already ran that, took 5 or so minutes. I'm running it on a fairly small cluster, so it's nothing crazy here. But that goes out, generates some data, and actually puts it in a place where I can use it. Okay, we'll get to the interesting stuff in a moment. And then finally, the final setup that we're doing is to then re-optimize it. So we've inserted a load of data. We're then running an optimize on it so that we can do a Z order. So saying I want to Z order by an ID. So we're not Z ordering by the key that we want to create a Bloom filter index on. We're just Z ordering by ID, collocate things based on ID. So we have these optimized files that contain collocated data around a one column, and then producing another index map on top of it going, and if you're looking inside those files, this is how you get to there for this other column. Okay, that's what we're doing. So we ran that, again, took 10 minutes, took all my files, took all my 100 million rows, moved them around quite a lot. So it used to be 448 files, it moved it down to 21 files. So it's made it a lot more efficient, it's combined a load of data, it's made it a much more efficient thing that I'm actually looking at. Okay, good. Now, one of the big tricks that they've put in there is changing the max file size. So a Bloom filter index, if you add a Bloom filter index and there's already data in the table, it won't go and work out the Bloom index for that data once it's already there. You need to either create the index and then add data, or do an optimize with the Z order, and then it will build out the Bloom filter index for the new files that are added as part of that function. If you have already optimized those files and you run an optimize over the top, it's not going to rewrite that data unless you change the max file size. And then it's going to force a rewrite of it. It's going to force a change of that index size. So they've included that as a little trick. So if you optimize it, check the index, look at those files, and then you want to rerun it and recheck it, you can just tweak that, rerun it, and it will actually do the data changes, and then you will get an updated Bloom filter index. So again, it's not really necessary to see how the index works, but that's in there just as a bit of a use case to see how things are fitting together. Still with me? Cool. Okay, so we now have the structures that we need. So we have sitting in here in our Bloom test, we've got a load of data. We've basically got two different timestamps of data, right? So we've got the original insert, and then you've got the after I'd optimized it. Because of course, we're using Delta, it will have logically deleted the original set of Parquet in the transaction log, but it won't physically delete it until I run a vacuum. So I've got the two sets of data in here. And for each of these Parquet files, inside my Delta index, so the Delta index is the folder structure that's added by the Bloom filter index. And that inside has a file that essentially relates to each of my Parquet files. And again, I've got two sets, one for before my optimize, one for after my optimize. And then, so annoyingly, they're not human readable. They are Parquet files. We need to open up and have a look at what's inside. But essentially, it is keeping these separate structures, this little binary index that I can go and read and say, should I look in this particular file, the Parquet file that relates to this index file, to find this particular record? And it'll essentially give me a yes or no. Do I need to bother reading that? Or essentially a probability index that I can then use to decide. Okay, so that's done automatically for me, right? So as soon as I've ran that single command of that create index, as soon as I've actually forced that index structure on top of that Delta table, then that management, the updating of them, the maintaining of those Delta index files is all done for me. That's now just a mechanism, the same as creating an index in a SQL Server. Okay, so let's go and have a look at what's actually in there. So I think we can go and have a look at the size of files, and we see they included this in the original notebook, and I don't really see, it doesn't really tell you much. So you can see there's a ton of files that were in there before I did optimize, and then after I've optimized, there's a load of files, fewer files, because I've combined and collated a load of stuff, but they're bigger. I mean, that's no real shock. The interesting thing, I believe, is essentially the Bloom filter index is the same size for everything. Essentially, you just get kind of the same number of files, but for the same size. So actually an index, a file saying this is the size of the Bloom filter index I want to create, this is how big it should be. And that's partly controlled by those settings that we had, that kind of number of items, that kind of thing determines the size of the Bloom filter index that we're going to end up with. So we've got this structure. That's what we see. We can go and have a look at what's in that file, and we get a little bit of information about it. It doesn't tell us too much about it. I think it would tell us more if we had it in the proper Hive one, but I didn't want to. But most importantly, we can get to actually running some performance tests. Does this thing actually help? Does having a Bloom filter index change anything? So, quick check. I've grabbed, just doing a quick select star from our test table, and say where the ID is 0, 1, or 99 million. I've reduced everything by a factor of 10 because I'm not using a billion rows, but still, we're essentially saying, give me a few records where I'm pretty sure that because we've Z-ordered by ID, that hash and that hash are not going to be in the same file. Because we've Z-ordered, we've kind of said, well, the min-max of those, the min-max of those, we know they're going to be separated, so we're pretty sure that we're actually asking for different things. And then we can use these hashes. We can essentially say, this is our dummy record, this is what I want to query on. So remember that we've created the Bloom index on this SHA key. So the other columns, if we're looking at string 1, if we're looking at SHA-1, SHA-2, 256, any of those other ones, we don't have an index on those columns. So there's a couple of things. So I've quickly ran these in advance. So doing a select count star from my Bloom test, where SHA-1. Now remember, that is not one of the columns that we have either Z-ordered on, and we have not written a Bloom filter index on that column. So essentially, we're getting no performance benefit from the Bloom filter index at all, and that took 33 seconds. On a tiny cluster, not too bad. Essentially saying, I want to go and find that record in there, and it just basically had to read everything. Or it might have done some kind of by chance data skipping by looking at the stats it had in the Delta transaction log, but it's unlikely. I pretty much had to read everything because everything might contain bits and parts of that. Then if we do that again and say, well, actually, I want to rewrite that query. Instead of querying on SHA-1, I want to query on SHA, I actually get 15.48 seconds. So suddenly, I'm actually achieving, it's basically cut my query time in half. I've had to read a hell of a lot less data because it's looked at it and gone, well, based on my index, I know I don't need to read that data. I don't need to read that data. I can focus on these files, which is great. So essentially, I have optimized my query. Now, essentially, kind of shaving off half the time of the query, that is pretty good. That's a nice improvement. And then the other side of things, saying something, I want to filter something that isn't there. Now, the example they had, they took that same hash that we're looking for, and they just threw an underscore at the end of it. Make up a new number, give it some random thing that doesn't exist, and we can run that query, and then we see 9.31 seconds. Because that's the index of saying, definitely not in that file, is very efficient. So currently it's done that. It's done a scan of my Delta index. It said, right, which files definitely don't have this value? And it's gone, all of them. And essentially it's just not had to read a ton of data. Therefore, it can run very efficiently. So we've got those three different scenarios that we're looking at. The times when we queried on a column that the index doesn't cover, that's not really going to help it at all. There's no benefit there. Times when we query on the Bloom filter indexed column, and that's much more efficient. It's going to go and find the data. It still has to do some data reading. It still has to open up a load of Parquet and actually bring it back. There's still some time associated, but you're getting efficiencies there. And then where you're looking for something that doesn't exist, really efficient. It's much more confident. It doesn't have the false positive thing. It's like, no, definitely not in there. And it's much, much, much quicker. So Bloom filter indexes, where you've got users who are coming in writing that kind of query, and especially if you're exposing your Delta tables to end users who are writing analytics queries, who are trying to query it, and you don't know what they're going to query, then actually building these index structures suddenly makes a hell of a lot of what they're doing much, much faster. And again, creating it and maintaining it is just that. Create index on Delta table. Nice and easy. Cool. So that's the general process. That's kind of how they work. And I got a little bit interested. I was like, what actually is that? What are you strange Parquet files? So I dug a little bit into it. And essentially, I dove into my Delta index. I grabbed one of the Parquet files. I pulled it out into a slightly separate thing. So I just threw that as a separate Parquet file so that I could query it and say, what are you? What's in there? So inside that Parquet, you get Bloom filters as a struct. And then for each column you've indexed, you get essentially a large binary object. So we say, what does that look like? If we just quickly run that again, we can do a df to display. And actually, the object that it has in there is way too big to display. So you'll see I'll get like a little fragment of it. You can see kind of what it looks like, but you don't get too much info in there. I'll take a moment to read my nice small thing because I've just turned this cluster on. There we go. So essentially, for each of the columns that you have your Bloom filter index on, you get just a giant binary object, which is essentially the kind of a B-tree map of all the things that might exist in that file, or will definitely not exist in that file. So essentially, each of the columns that you've indexed on, you'll have more and more objects in this struct. And then I had a bit of a play to say, could I actually sort of see more of that? And you can export it to CV. You can play around with that data. It's not that useful. So playing around with it, not particularly great, but essentially just knowing that on a one-to-one mapping for each of the Parquet files that you have inside your Delta table, you'll have a mapped index file created per Parquet file in your table that has essentially that structure. And kind of the same way that it works in a SQL server, but you don't see the files in a SQL server. Essentially, it's just creating and maintaining index objects. Obviously, be aware that there is an overhead here, right? The same as, if you go and look in a SQL server, and I know I keep banging on about it, but it is essentially the easiest way for a lot of people to understand that comparison. If you create a non-clustered index on every single column in a SQL table, suddenly performance goes terrible. Because actually, anytime you put data into that table, it has to go and update a load of these different maps, and it's really, really slow. So the more things that you index on, and the more accurate you want that probability, and the more items that you cover by it, then the slower then an update becomes. So Bloom filters are great for increasing performance and really targeting the kind of columns that people are going to write very selective queries on. So if you have a big, huge, deep table and people keep going in and searching for a given ID or searching for a dimensional key, if you're doing things like that and it doesn't make sense to have partitioned on that key and it doesn't make sense to have Z-ordered on that key, but you still want to have some kind of performance gain, then getting a Bloom filter index and putting it selectively on that column, great idea. It'll really help and it'll really, really increase performance. But it will slow down ETL a little bit. Definitely don't go away and create a Bloom filter index on every single column because that's just going to mean ETL becomes really slow. Getting data in there is going to be really, really slow. You're going to have tons and tons of files to maintain and it's not going to go that well. So use it judiciously. Use it on the bits that really need that performance hit. And it's one of those things where, I guess, like a lot of things in the lake, you can create an object and then you put it out in the world and only then do you discover how people are going to use it. That is the bit of a danger. So remember, if you create a Bloom filter index on top of a table that already exists, you do need to run an optimize and a Z order and that kind of thing to rewrite the data, which then forces the writing of the Bloom filter data. So bear it in mind. But otherwise, yeah, let me know what you think. Let me know if you're currently using them. Let me know if you're not using them and you've just gone, oh, I should really be using that. Because that's what I did when I first found out about them. So I think that's it. As always, let us know down in the comments what you think. Don't forget to like and subscribe if you are new around here. But otherwise, we'll see you again soon. Cheers.